Good morning, everyone. My name is Hugh. I'm from Singapore University of Technology and Design. First, I want to say sorry that I cannot attend AAAI to present my paper due to visa issue. So here's a video recording of my presentation. Hope you enjoyed the presentation. Today I want to talk about our new research, a novel cross-domain descriptor for 2D 3D matching for an LCD. This is a joint work with Michael Angelinawi, Linh Sơn Hứa, Đức Thành Nguyễn, James Maroy, and Sakit Yon. In this paper, we will focus on the problem of local matching between 2D and 3D data. Let me give you a small example. Suppose you have two images captured at different viewpoints. The goal of a local 2D descriptor is to encode the local region of the image into a vector of real values. This vector should be repetitive enough so that you can establish a good match between them, while also discriminative enough so that you can avoid false positive matches. The same case can be said with 3D data. We have two scan point clouds captured at two different viewpoints. The goal of a local 3D descriptor is to encode the local geometric region of a scan into a vector of real values. Then we can establish correspondences between point clouds. These tasks have been around in computer vision for ages, and there have been a lot of good solutions proposed for both 2D and 3D matching. Now let's look at the example a little bit closer. We see that the 2D and 3D descriptor are represented by the same underlying local region, the corner of a chair. However, due to differences in representation and algorithm, the descriptor of 2D and 3D are essentially different. This makes matching them virtually impossible. While 2D and 3D descriptors are widely available, finding association between these representations is a challenging task. In general, there is a large disparity between 2D and 3D representation. Data in 2D or images can simply be represented by regular grids. Meanwhile, 3D data can be represented by either meshes, volume, or point clouds. Even with the recent advent of deep learning, these issues remain the same. Features learned on 2D domain may not be applicable in 3D space and vice versa. In this work, we attempt to bridge the gap between 2D and 3D descriptors by proposing a local cross-domain descriptor that works on both 2D and 3D domains. To grab such descriptor manually is a very difficult task. So here we employ a data-driven, self-supervised learning approach, where the descriptors are learned from 2D, 3D correspondences. Our descriptor is also highly efficient and has a wide range of applications, which will be shown later. To give a little bit of perspective, let's consider all of the works about local descriptor up until now. First, we can divide the length of local descriptor into 2D and 3D domains. Second, we can further classify the descriptor by their approaches, either handcrafted or learned. The upper left quadrants give us a handcrafted 2D descriptors such as zip, sharp, ARP. These are very popular descriptors and have been well studied in the earlier days of computer vision. Similarly, the upper right quadrant contains traditional handcrafted 3D descriptors such as FBFH and SHOP. Recently, deep learning has been applied for end-to-end learning of descriptor. The robustness of the learned descriptor over the handcrafted ones has been proven clearly in several experiments. Some notable works are Deep Dash or Lift for 2D and 3D Mesh and FCGF for 3D. In this context, our proposed Learn Cross-Domain Descriptor called LCD can be used in both 2D and 3D tasks, while also support cross-domain matching, providing a bridge between 2D and 3D descriptors. LCD is one of the first general descriptors for both 2D and 3D domain. Here we come to the key idea of the paper. Let Y be a color image back in RGB color space. Similarly, let P be a local color point cloud, represented by its coordinate and RGB color. Our goal of learning a cross-domain descriptor is to find two mapping F and G that maps the 2D and 3D data into a shared latent space. If Y and P are correspondences, we want their embedding to be as close as possible. On the other hand, if Y and P are not a match, then we would want to push the embeddings further away from each other. In addition to mapping data to descriptor, we also aim to learn the inverse mapping function F prime and G prime. As later shown in our experiment, these inverse mappings are beneficial in downstream applications as part to dense depth estimation. Here is a detail about network architecture to learn the local cross-domain descriptor. For the 2D branch, our 2D autoencoder takes input a color image backups and process it through a series of convolution with ReLU activation in order to extract image features. For the 2D decoder, we use a series of transpose convolution with ReLU to reconstruct the image batch. For the 3D branch, we adopt the well-known PONET architecture, employing a series of fully connected layers and smart bundling to calculate global features. To reconstruct the color point cloud, we employ another series of fully connected layers, which output a color point cloud. To enforce a shared representation, the two autoencoders are tied up between their bottlenecks by optimizing a triplet loss. In addition, we also optimize the photometric loss and transfer distance between the input and reconstructed patches. The final training loss is a combination of photometric loss, chamfer loss, and triplet loss. Our network requires a dataset of 2D, 3D correspondence to train. To the best of our knowledge, there is no such publicly available dataset. Therefore, we build a new dataset of 2D, 3D correspondences by leveraging the 3D dataset from RGBD scan. In this work, we use the data from 3D Mesh and CNN. 3D Mesh dataset is a collection of existing RGBD scenes from different worlds. CNN is a comprehensive indoor dataset scanned by handheld RGB sensor with fine-grained annotation. Our training dataset consists of 110 RGB scans in total, of which 56 scenes are from CNN and 54 scenes are from 3D Mesh. The remaining scenes are used for testing and evaluation. The 2D and 3D correspondent data is generated as follows. Given a 3D point which is randomly sampled from a 3D point cloud, we extract a local batch from a radius. To find 2D 3D correspondence, we reproject its 3D position into an RGB frame for which the point lies in the camera system, taking occlusion into account. We then extract the corresponding local 2D batch around the reprojected point. In total, we collect around 1.4 million correspondences, with varying lighting conditions and settings. We first evaluate our descriptor in a classic 2D computer vision task, image matching. Since we are only interested in the performance of the descriptor, to give a fair comparison, we use the same key point for all of the descriptor. Matching between two images is done by finding the nearest neighbor. Our result is shown on the right-hand side. Compared to the result from SHIP on the left-hand side. You can see that our descriptor can match between regions with repetitive texture, whereas SHIP fails in this case. Overall, our descriptor gives state-of-the-art performance when comparing to other handcrafted descriptors as SHIP and SHOF, or learned descriptors such as Superpoint. For our second application, we demonstrate another practical use of our descriptor by combining it with RANSAC for the 3D global registration task. Given two 3D fragments from scanning, we uniformly downsample the fragment to obtain a key point. For every key point, we form a local batch by taking points within a neighborhood. The 3D descriptor are then computed for all of the key points. We match the two sets of key points with nearest neighbor shot and use RANSAC to estimate the final ridge transformation. Here is a qualitative result on the 3D match benchmark. Our method is able to align pairs of fragments with different changing scenarios by matching local 3D descriptors, while 3D match fails in cases when there are ambiguities in geometry. Here we show the record of different algorithms on the 3D match benchmark. We compare our method against other handcrafted and learned descriptors such as FBFH, 3D match, and 3D SmoothNet. Even though our descriptor is not fine-tuned for this task, it is still on par with 3D SmoothNet and outperforms other methods by a good margin. We further evaluate our local cross-domain descriptor with 2D 3D place recognition. Our task is to find the corresponding 3D geometry submap in a database given a query 2D image. We only assume raw geometries are given without additional camera information, as often seen in the camera localization problem. We cast this 2D 3D place recognition problem as a retrieval task. For each 3D submap, we sample descriptor on a regular voxel grid. These descriptors are then aggregated into a single compact VLAT descriptor. We follow the same process on the image to extract the descriptor, but this time on a 2D grid. The query descriptors are matched with the database for retrieval. Here we show the representative top 3 retrieval results. On the left, we also plot the fraction of correct queries for different values of candidates as shown on the right. Our local cross-domain descriptors are highly effective in this 2D to 3D retrieval task, achieving over 20% recall within top 10 candidates. One advantage of using autoencoders is we can transform between 2D and 3D domains, as we have the inverse mapping already learned. Here we show another application called sparse-to-dense estimation. Given an input RGB image, we randomly sample local image batches. From these 2D batches, we first encode them using the 2D encoder F and decode using the 3D decoder G prime to reconstruct the local point clouds. We assemble this local point cloud into one coherent point cloud with a hairless sparse depth samples. Finally, the dense depth prediction is calculated by projecting the dense 3D point cloud back to the image plane. Here we compare our method against FCRN, another state-of-the-art single image depth estimation method. Our descriptor outperforms the current state-of-the-art by a large machine. To give a better understanding of our descriptors, we visualize them together by mapping high-dimensional descriptors into 2D using TSNE embedding. We extract all local batch in a scene, pass each of them through our network, and determine its 2D coordinates using TSNE embedding. We then visualize the entire batch at that location. As can be seen, batches that are corresponded to a structure or object in a scene are well clustered together, which explains our good intra-domain matching performance. To prove that our descriptor can perform cross-domain matching, we visualize descriptor between different domains. For all of the local batches in an image, we extract the local descriptor and perform dimensional reduction with BCA. We then assign a color based on that value. The same is done for the corresponding 3D fragments. The visualization results show that not only our descriptors are very similar in 2D and 3D, but the descriptor can also differentiate object boundary really well. So to summarize, we propose a new local cross-domain descriptor that encodes 2D and 3D structure into representation in the same latent space. Our proposed descriptor can enable unique cross-domain application on top of common 2D and 3D applications. Our code and datasets are released publicly and can be found in the link below. Thank you for your attention. If you have any further questions, please send me an email.